Hello YouTube, De-bodgery here, aka Richard Gumfaw on Facebook. Welcome to EV Components Review. This is the upper stage, or the logic board, for a Surron controller. And here is the power stage. So over here you've got a high voltage DC to DC, so it's taking basically that 60 some odd volts from the pack and dropping it down to like 12 volts. And this is only a dual voltage board. So this is probably like a 5-volt linear regulator. There's no other DC to DC or linear regulators on here at all, so most likely this CPU over here runs off of 5 volts. So I don't see a linear regulator or anything else here anywhere. And probably all these support components, they all run off of 5 volts as well. Probably like the gate drivers, which are down here, those probably run off of 12 volts. Anyway, yeah, it's simpler than a lot of stuff I've seen as of recent, because they almost always have like 12 volts, 5 volts, and 3.3 volts. It is nice to see that there is some protection components here right around the connector. So, you know, this used to be plugged in there, but I cut it off. It was buried in potting until I got it loose. So I just figured I'd cut the wires off and call it a day. But yeah, so seeing protection devices in here to protect these pinouts from extraneous calamity happening. That's nice to see. These two connectors right here, those are, you know, pin headers that came down to here, and these two pin headers used to be like right there, and that's basically doing stuff like sending, you know, gate control signals down to here, and not much else. Yeah, the potting that was inside this connector was not cooperating. I'd heat up the board, but the pins just would not come out. So anyway, instead they pulled up from the board, but at least it didn't rip up any traces, just the solder joints failed. So that's kind of cool. Most of the time you rip up traces like these little ones, like I did on that eBMX. On the back side of this board, and this is also true for the front side of the board, so you've got these four standoff through hole places right here where 4 screws go down, and that bolts battery minus from these standoffs right here to here. And this is a current path, by the way. I'm not super fond of current paths this way. This really ought to just be ripple filtering, but no, this is a real live and important current path. And right here, 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 and here, that's battery plus, and that too is a current path. So not an awesome design. These are supplemental to the ones that are actually on the power stage, and they are on both sides of the board. So like you can see all these little vias through here, and all those vias in there and stuff. Yeah, that is because there is more copper on top of here and all across the backside here and around there. So it's good from that perspective, because there's copper on the top and the bottom of the board that's beefing that up some, and the same thing is true for battery minus. Like you can see all those vias in there, and they are also on here too. So yeah, there's 2 pieces of copper on the top and the bottom of the board that are reinforcing each other. So for this controller, because it's not really that powerful, it's probably enough, but it's not awesome. I definitely don't like seeing this sort of thing, because this really ought to be just ripple filtering and not be a primary current bus, but it is. Anyway, there's all your capacitors. They are 80 volt, 470 microfarads. Here's your CPU. Here's a current sensor. There was another one there, but it came up with the potting. Yeah, a couple other support chips. That's pretty much everything that's here. And here is the power stage. Pick this up. So, like a lot of the stuff, these two board designs, this is an MCPCB, or metal core printed circuit board, so it's got aluminum back on it. Very good for heat transfer. And these are, for all intents and purposes, TO220 MOSFETs, just with the top clipped off and then soldered down. So as far as heat transfer from these MOSFETs to the aluminum, it's actually pretty darn good. It's every bit as good as, like, say, the tall packages. But current path out is through a MOSFET leg rather than through like 5 or 6 of them that are soldered down. So current carrying here is a lot less than it is like in the tall package. But physically the package itself is about the same size. This is lacking in ceramic capacitors. It's got 2 here and 2 here, and I would really prefer to see like 4 here and 4 here. You can't really put them anyplace else because it's designed. So they're pretty close. You know, I'd kind of like to see them more closely oriented. Like this is low side and this is high side, so I'd like to see like 2 here and then 2 more over here. These 2 here are kind of filtering for this side of this one and that one there, and also for here. So if like put 2 more there as well. So yeah, that's where you would account for. I guess you'd account for more like 6 more, or yeah, just 4 more. Yeah, 2 here and 2 here. That would pretty much account for most of the noise in here, high frequency wise. This is kind of annoying. So I don't know if this was like battered solder work, flimsy solder, something like that. But those 5 right there, here, here, and here, and yeah, oops, that's the wrong one. So the smaller ones were these little standoffs, and they're threaded, and then the larger one was this. So this used to be in the middle right here, and then there was a bunch of these all distributed around on the board like this. So yeah, I don't know if like the upper board was putting stress on these little standoffs and it was slowly pulling them off, or if something else happened, but the board was hot and it was inside the heatsink, and the potting was fairly soft at that point, and nevertheless these all came off with the potting. So I thought that was sort of strange. That meant that these were more or less kind of sitting there and not really connected to anything, which is disconcerting to say the least. Yeah, they literally came away very easily, and yeah, I had to dig them out of the potting instead of them being stuck to the board. Because they should have stayed put. You know, the soldering on them should have been enough to keep them in place when I was peeling the potting away, but that's not how it happened. Yeah, I would have to say that probably they were just barely holding on, and that's not good. Yeah, that's definitely not good. Yeah, it may also have been that they just simply starved for solder, because there's very little on the board, and then there's like none on the actual standoffs that have the threaded hole. So that may have been also why they pulled away. All right, so all across here and here and here, this is all battery minus, and that all comes up, and the screws that were in the board, you know, so that ties those together, plus we've got lots of vias in there, and that's all battery minus, and of course it ties all this together too, and that's all battery minus. So for the amperage of this controller, I would say probably this much copper is enough. You know, and it's a fairly large current path. So battery plus, oh, and by the way, battery minus, here is, it had a tall standoff like here, and then there was a cable that went from here over to this other standoff right here. So that's how battery minus got over to there. And battery plus, so here's its standoff, and then there's copper all across here and here and here, and then of course on the back side of the board you've got, you know, this whole path here, and across the top as well there's that same copper. So again, for the application and the power of this board, it's probably enough, but I really like to see, you know, solid copper buses with reinforcing, like from this stud all the way around here, all the way around here, all the way around here, and not depend on the logic board for that stuff. That should just be ripple filtering, and that's all, and it's not. This is an important piece of the current carrying bus. I would say at least 50%, if not more of it, goes through the bottom side of this, and then the other portion is right here on the circuit tray. So if this was burned up, I would say there's a fairly good chance that those traces would probably cook as well. Yeah, pretty good chance. Like that thin spot right there, that would probably cook, and there's a thin area there and there, so probably those areas would probably like burn through, and this would be very much like what I've seen on the KO controllers. They also do the same thing. You know, the battery plus trace on here cooks and burns through. Anyway, yeah, it's an okay-ish board. It's not awesome. I would say definitely don't waste your time trying to upgrade it. It's just not worth it. Yeah, the potting alone makes that really hard. If it wasn't potted, I'd say sure, but you know, adding the potting in it, there's a good chance you're going to damage the thing. This stuff down here, this is your gate drivers. I don't know which gate driver goes to which set of MOSFETs, but yeah, there's 3 sets of them, and of course you got 3 phases, and this is an 18 FET controller, so yeah, that's where those go. It's interesting that all the gate drivers are down here. My thinking is they probably get kind of warm, and that's why you put them down here. I would rather have seen these 3 MOSFET banks distribute a little bit more evenly with some better copper around them and things like that, because like even the phase buses don't have any reinforcing in them, which is meh, not cool. Yeah, one little detail I want to point out before I call this video done, and that is you can see these traces that are pulled up. So this, of course, is a metal back PC board, and you can't make vias in there. So if you look here, these pads right here, there's vias that go through the board, top and bottom, knits all that stuff together pretty nicely. With a board like this, you can only have a single layer on it, and there's no reinforcing here. So these pads will rip up like you see here. And in fact, you know, that stud used to be, you know, soldered down to one of these positions. This whole area here was pretty deeply buried in potting, and so to get the plastic and all that stuff off, the studs came up too, and as a result it ripped up the circuit traces. Well, this is exactly the problem that you'll have with like the KO controllers, because the studs are just simply soldered right down to the circuit board, and it's on that very small area, and this is very similar to the KO controllers. Whereas like say the EBMX, they've got whatever that was, I forget it was, you know, 14 millimeters by 15 millimeters of surface area that they're soldered down to. So, you know, you've got a lot more support. This little stud, you know, just doesn't have enough, and as a result, it rips up the trace, and then the board is trashed. Like we care about this, but, you know, a KO controller costs $1,000, and this doesn't. You know, this is a much cheaper controller, but yeah, you're going to have that same problem. And that's why you shouldn't crank on those studs, you know, with a screw, because you will literally twist them off and then you'll rip up the solder pad like that, because there's just no support here for them. It's not a very good design. And the proof's in the pudding here. You can see the same thing happening. And this was just simply trying to pull these up through the potting that I'd partly picked away, and they broke off like this. So, yeah, I don't recommend that design. It's definitely weak. Well, I think that's all I want to show for the Surron controller. The next video I do for it will be looking at all the components, and that'll probably be 2 videos, one for the logic board and one for the power stage, where we get to look a little bit more closely under the macro lens at all the components. Alright, I think that's it.